the into the skeleton file, then what you want to do is recreate your non-design space as regular solid geometry. Once you've done that, you want to then begin working with what are called work sections to try and understand what the topology really represents. And then you want to create parameterized cross-sections that represent the topology. And those parameterized cross-sections, you want to then use those to either sweep or revolve regular solids that get united together. And then you want to relink those sketches and those solids to your assembly parameters. And the relinking is either waiving the geometry or publishing the geometry if you're on Visio. So we're going to kind of take each of those one by one. So if we look at the layering, this is just out of the recommended documentation for NX. NX says that layers 1 through 20 should have solid geometry. Layers 21 through 40 should be sketch geometry. 41 through 60 curve geometry, and so on. I am recommending that if you import IGES, you put it on layers 121 to 150. If you input, if you bring in like STL data, you could bring the STL data also into 121 to 150. As you're creating section cuts through this geometry, the section cuts are really reference geometry, and those things ought to be created. Those section cuts should be created on section 61 through 80, and that will greatly help organize these files so that you can easily turn off layers and have things disappear. Eventually, you're going to want to hide the IGES, and so you can just go in there and turn off layers 121 through 150, and all of this tessellated data will just disappear. So here's an example of a simple skeleton representation of the A-arm, or a connecting arm. It has a length, it has a couple of widths to it, and that could easily be the skeleton that you open initially, and then we're going through the process of importing IGES. So on top of this model, we then go and grab our IGES file, and we make sure that we switch. So this is an important step for the NX folks. As you're importing IGES, you can actually bring up the file and find it, but you need to also tab over, oops, went the wrong way. You need to tab over to the advanced tab, and you need to make sure that you bring in smooth B surfaces. That's the check you want to make. Otherwise, you're going to get just line data, and point data is going to come in. You're not going to get any surfaces. So you need to make sure that you do that. And it should bring in this IGES model on top of your skeleton. Once you have that skeleton brought in on layer 61, or excuse me, not 61, 121, then what you can do is begin to take work sections through the part, and these work sections for NX are turned on by the icons that you can see that are highlighted at the top of the toolbar. There's a plane that has kind of an XYZ axis that has been highlighted, and then there's also the working coordinate system that's highlighted. that working section or view section, if you turn that on, it allows you to define XY plane, YZ plane, XZ planes that you can use to cut through this data. And as you cut through this data, you can also ask it to create for you these section curves. Those are the highlighted blue curves that represent where this part has been sectioned at. Now, those blue curves, I would not try and use directly. Those are only intended to be kind of references as to what the cross-section looks like at this particular cut. If those are put on section or on layer 61, you can go in there and reference those when you go into a sketch, and you can create a sketch that is more manufacturable than these very rough cross-sectional cuts. Trying to make my mouse move and it's not moving, so I'm going to try and plug in my regular mouse. So hopefully you can see where my mouse is moving. Larissa, are you able to see my mouse there at BYU? Is that coming through?
Yeah, we can see it.
Okay. So these very rough cross sections are not very manufacturable. They only give you an idea as to what the shape needs to look like at this particular cut. And so I would go ahead and create these sections, use them only as reference information when you create an actual sketch, a traditional CAD sketch that is fully constrained and much more manufacturable than these cross-sectional curves that is done by this work section. So here's another cross-sectional cut that is very funky looking here at the back. That could just as easily be a rectangle that is this long and as wide as the widest point. And so that would just be reference kind of data. Here's a cross-section cut taken the other way. So I just told it to give me a different plane, and you can actually grab these handles and slide them in and out, and as you slide them in and out, the section plane cuts at different locations. But wherever you want, you can actually tell it to save a set of cross-section planes. And the way you do that is click in NX, you click this button that I'm hovering over right here, which will create these blue curves as permanent section curves, working curves, but you're going to want to create those and keep them on a reference layer. So once you have kind of analyzed this tessellated model, what you want to do is come up with a CAD part that is manufacturable. And so again, from our last lecture, here is an example on the left of a optimized hypermesh model, which is not manufacturable. And hopefully you can look at the example on the right and you can see where they've used simple cylindrical extrusions. They've used simple yet manufacturable sketches to do extrusions to build the representation of this bracket. And yet the bracket, the finished bracket that looks nice, does in some respects mimic the structure that OptiStruct gave. What industry has found from using topology optimization is that you would, if you remember the original design space for this bracket was just a big block, and you would not initially be able to, in your mind, know where the load paths are going to go through that block until you have it kind of do a topology optimization. Once you now see those load paths, so on this left side, there's a load path that follows this kind of structure, this, you could call it almost a truss-like structure. Once you see that as an engineer, then what you need to do is be able to say, okay, I need to build a part that's manufacturable and looks something like that, where just initially you're not able to kind of predict that. And so the goal of kind of this week is to bring in an optimized part and kind of remodel it into something that is manufacturable. Here's another example from last lecture. On the left, we have the optimized part. We talked about it not even having a support structure running down this left-hand side where the mouse is. As an engineer, you would look at that and say, that's not believable. And so as an engineer, you are going to want to come down and say, okay, I need another structure on the right-hand side of this, and you're going to build it so that it's somewhat symmetric about this open area that does not need to be there because no stress is passing through that space. But again, the challenge and the goal is to build something that is a significant reduction in weight and yet provides plenty of support for any of the load that is passing through the object. And here is yet a third part. If we look at the top of the topology optimization, we have this thing just floating out in space. That thing that's floating out in space is part of our original non-design area. There's an attachment point that has to be there. And as an engineer, you say, that's total nonsense. You need to somehow build a manufacturable part that has that non-design space still attached to the overall structure. You'll also notice on this that this center area doesn't have a lot of the geometry taken out of it. If we were to dial the density function down even more, the center area would disappear more. And by watching it kind of disappear, it would give us some kind of a feel for what that part is. So even though we output only one representation of the optimized part, you can play with that slider bar inside of OptiStruct to kind of watch how this part gets reduced. And by watching that, it will give you some idea as to any kind of webbing or any kind of internal structure that needs to be kind of added to the part. And so again, the goal of this week's lab is to really kind of appreciate and understand how to come up with a manufacturable type part. So once you've completed this week's exercise, how do we take this and what do we do with it? How do we apply it to the project? And so the last couple of slides that we have here really just talk in terms of now taking this and taking it and applying it to the project. So here are my recommendations. Each team member picks an appropriate component to do topology optimization. And so from previous lectures, this is an illustration of all of the components that kind of go into the car. We've talked in the past about how maybe topology optimization of the main chassis, topology optimization